Chapter 5, Section 2. So this section, we're going to use exponential growth model. Remember last class, we talked about exponential growth and the decay. Right? So we're going to use this model to talk about compound interest. So which the financial institutions or the banks offered type of kinds of interest rate. So we deposit some money into the bank. Bank normally offers some interest. So there are a couple models. So the first one will be called a continuous interest rate. Remember, for exponential function, the differentiation of the function always involves the original function. So in this section, we're going to use this equation. Right? Amount of money after T years equals to the initial deposit. Right? Remember this P naught represents the initial value, which when T equals 0, right, the function value will be P naught. So when you first deposit this amount of money, after T years, how much money you have in the account. That depends on the interest rate and also the number of years. So this R here represents the interest rate. And normally it's the annual percentage interest rate, right? Oftentimes when you're passing a bank, you see that saying, okay, if you deposit CD, that offers you APR 3%, so on and so forth. Means annual percentage of interest rate. So we're going to use this, and the E is our old friend, right? E is Euler number. It's a constant, equal to 2.71a, keeps going on the digits, but the calculator just returns you a rough approximation. So let's see this example. So continuous compound interest. So what does compound mean? Compound means you calculate the interest according to the interest rate and time. Then you add this interest to your initial value. So then this becomes the initial value for next compound period. So your principal, right? Your principal. So your interest also earns interest. So you keep adding on. So the interest will put on top of your original investment. Then this your initial investment plus this interest becomes your principal for becomes your investment for next round, right, when the interest is being calculated again. So this keeps going. So this is called a compound. So compound continuously, seeing the second you can think of it, the interest is already being calculated and it's already being added to your principal. So continuously. So later on, we're going to see more clearly this Euler number. Okay, what does this Euler number do? The Euler number basically is like a bridge from a finite world, right, to an infinite world. So we'll talk about more about this, right? Okay, let's see this question. So we deposit $1,000. So this is P naught equals to $1,000. We don't have to carry the dollar sign when we do calculations. It's invested at a 5% interest compound continuously. So the little r equals to 0.05. right? That's equivalent value to 5%. So 8, give the formula of AT. So amount of money after T years. The compound amount after T years. So which is initial value, which is 100, multiplied by all the number, E, raised by R times T, 0.05 times T. That's for 8, that's it. So after T years, the money staying in the account would be calculated this way. Or 1,000, not 100. $1,000 initial value multiplied by E raised by 0.05 times T. Okay, B is asking how much will be in the account after 6 years. So that's asking the amount of money in the account after 6 years. So we just plug in T for 6. That's 1,000 times E raised by 0.05 times 6. Okay, that's 1,000 times 1,000. Oh, I made one more zero. Multiply by 0.05 times 6. 5 times 6, 30, but we have decimal point, so the E raised by 0.3. So when you put into a calculator, be very careful, okay? You can press 1,000, press open parentheses, then E raised by 0.3, or you can calculate the E raised by 0.3 first, then you multiply by 1,000. All right, so I'm going to do on my calculator, I'm going to calculate the E raised by 0.3 first. So my calculator, I have E, then I find out how to do raised by, oh, that's squared. So you need to have, you have to find these red buttons, all right? So E raised by, where is the raise? Different calculators have different symbols for the exponents, or maybe this one, x raised by y. Okay, raised by 0.3. Right, for my calculator, I say x raised by y. So E raised by 0.3, then I multiply by 100. Right, so I get 100. Why I always say 100? Multiply 100, 1,000. So $1,349 and 99 cents. Because what I have on my calculator is 1,349.858. But for money, we only go up to cents. So we only have to cap 2 decimal digits. So what we do is after this 5, the number is A, we just carry on to 5, change 5 to be 6. So this is 86. So 1,000, now I can carry on a dollar sign. $1,349.86. Right, so that's after 6 years. So the total interest is 349.86. So as you can see, this is a very powerful formula, right? 6 years, you can grow money so fast, more than 30%. It's about 34, 35% of the money. Okay, so see, after 6 years, at what rate will A of T be growing? Actually, the textbook has all the answers. We could just follow that, because for me to write down this is very difficult. Okay, you see A, we just plug in A of T. We have A of T equals 1,000 times E raised by 0.05 T. And for B, we just plug in 6 for T. So we do E raised by 0.3 first, then we multiply by 1,000. So we get $1,349.86. So C is asking the rate of change. So rate of growth is different from interest rate. Interest rate is fixed at 5% and does not change with time. However, the rate of change, remember rate of growth or rate of change is a derivative of the function. So when we take the derivative of this, what do we get? we get a 1,000 multiplied by 0.05, then multiplied by e raised by 0.05t. So 0.05 times 1,000, that gives us a 50, right? 50 times e raised by 0.05t. Then after 6 years, we just plug in 6 for the derivative of the function. Then we get about $67.49 per year. Okay, so this is asking what rate. So what kind of rate of change A of t is growing? As long as we see the rate of change, rate of growth, rate of decay, we know that's the differentiation of the function. So we have D, how long is required for the initial investment to double? So A of t now equals to 2 times the initial value, 2 times the 1,000, which is 2,000 now. So we want to find out in which year, how many years later, the amount of money in the account will be doubled. Okay, so just set the function equals to 2,000. Then we divide by 1,000. So we get this, e raised by 0.05t equals 2. Then we take a logs on both sides. Right? Then this is 0.05t comes down to the floor. The ln becomes 1. So 0.05t times 1, still 0.05t, equals ln 2. Then we just divide by 0.05 on both sides. So ln 2 divided by 0.05. So in our calculator or on our calculator, we just press in ln, where you can find ln, then press 2, then divide by 0.05. So get about 13.86 years. So about 14 years. So the money will be doubled about 14 years. Let's see how we use this in other life applications. So Picasso's The Dream was purchased in 1941 for a price of $7,000. So 1941 was war distressed. The painting was sold in 1997. How many years later? 36 years later, for $48.4 million. The second highest price ever paid for Picasso's painting at auction. So this is asking, what rate of interest compounded continuously did this investment earn? So this is looking for the rate of interest, R. Yeah. It didn't say the rate of change, the rate of growth or rate of decay, right? The rate of interest. So looking this, the R, remember in the formula, we have this. We have this, right? So this is looking for the rate of interest being compounded continuously. So looking for this R. Because we know the year, right? 1990, from 1941 to 1997. So, yeah, so we rewrite 7,000 as 0.007 million, because once we do the calculation, put in the equation, the units has to line up. So the initial value was 7,000, right, as 0.007 million, or you can write 48.4 million as 48, comma 400,000. There would be too many zeros, right? So this is a 48.4 million. You can either convert this into dollars or you convert the dollars into millions. So in this case, we convert dollar into millions. So we have 0.007 million for $7,000. So the initial value was 0.07. Right, so we just plug in and we are given this about 48.4 million. Right, after 56 years. So 1997 minus 1941. Right, 56, not 36. 56 years. So I have this 56 years. So set up equation as the function is 0.007 e raised by r times 56 equals 48.4 million. We divide by 0.07 on both sides. So we get e raised by 56 times r, about this amount. Then we take ln on both sides. Right, so ln, then we're able to pull this r, or 56r, down to the ground. Then ln e just becomes 1. So the other side we have ln, about 6,900 something. Then we divide by 56 on both sides. So once we put into a calculator, we divide, we get about 0.158, not even 2%. Right? 0.158. So that's the interest rate. If we want to convert it into percentage, that's 15.8%, right? Which is a crazy return. Can you think about something, the interest rate at 15.8%? So that's another situation how we use the exponential growth equation. Okay, talk about bank or financial institutes offer us interest rate. And the two types of interest rate. One is called a simple. One is called a compound. So simple interest rate we see in governmental bonds or treasury notes, right? You just buy the face value, right? You just then when the mature date comes, you can get your money back. So your initial value, your initial investment plus the interest. But for bank institutions, they are mostly offering something called a compound. But the compound period could be different. Compound period. We're talking about compound continuously. Because continuously, we have this E. Right, so soon we'll see what is this E. So for now, let's just keep a question mark in our head. So compound continuously, we use this E. But the compound period could be different. Compound period could be weekly, monthly, yearly, even daily or bi-weekly, so on and so forth, right? Or daily. Then which formula we use? We're going to use this formula. So B may be representing balance. Balance after T years, we still see T here. We still see R interest. R is still annual percentage interest rate. T is still number of years, the money in that account. Now we have one more. Or P naught is still the initial investment. Now we have one more thing, M. M is a compound period. Okay, if it's weekly, M equals 52. But there are 52 weeks in a year. If it's monthly, M equals 12, because 12 months in a year. If it's yearly or annually, this is 1. Daily, 365. Right? Compound continuously, the whole thing becomes, so this whole thing becomes E. So soon we will see this, how is this related? How is E related with this? So compound continuously, this thing becomes E. But normally, if we have a certain finite compound period, if it's weekly, M equals to 52. If it's monthly, M equals 12. If it's annually, M equals 1. If it's bi-weekly, M equals 26. If it's quarterly, M equals 4. So on and so forth. All right, so that's dependent on the compound period. So now, so this is called differently. It's also amount of money after T years. So P naught still initial value, R still annual percentage interest rate, T still number of years, the money in the account. M is the number of compound period in a year. M equals 12 if it's compounded monthly. Because if you compound monthly, every month the interest will be calculated, then add to your previous principal. Right? That's one compound period. There are 12 such months, 12 months. So 12 such compound period in a year. So M equals to 12. Mm-hmm. Right. In the previous case, let's see, if compounded monthly, the interest rate is 6%, and the compound monthly means M equals to 12. Right? If it's for 1 year, like T is 1 year, for 1 year, right? Because the compound is 12, so we calculate, so that's this amount. But if it's continuously, it's a little more. We see this 0.84, 0.68. So the compound period, the more it's being compounded, the more money one's making. Okay, so let's see this table, this comparison. If you compound it annually, that's only 1,060, so the interest is $60. If it's compound quarterly, the interest is 61.36 cents. If you compound it monthly, 61.68 cents. Compounded daily, 61.83 cents. Continuous compounded continuously, the 61.84 cents. So the bigger the number of compound period, the more money of the investment. Negative interest rate, it happens, rarely. Remember this exponential decay. But the calculation is the same, just the exponent is negative. But you rarely see negative interest, right? So what is negative interest? So when the government don't want you to put money in the bank, when the government wants you to spend your money, right? Do not put in the bank. If you put in the bank, you lose money. So you need to spend them. Well, in this formula, they call present value. Right? Present value. Let's see this example. Suppose you want to invest some amount of money now. The present value, you have $5,000 in 2 years. Oh, suppose you want to invest some amount of money now, you don't know how much, so that you can have 5,000 in 2 years. So that's money in the future. So in the future, you have $5,000. Assume you can earn 12% compounded continuously. How much would you need to invest now? All right, let's go back. Now I understand why this textbook called this. Let's study this formula. So this is the present value. This is the present value. This is the future value. Let's rewrite this one. Let's divide this term on both sides or multiply, even multiply. Let's multiply e raised by RT, positive, on both sides. Then these two terms, you see we have e raised by negative RT plus RT. That's e raised by 0. That's 1. So 8 times 1, which is 8. So that's why this formula is equivalent to amount of money equals P, present value, times e raised by RT. Okay, so there's nothing special about this equation or this formula. It's just rewriting the previous exponential growth formula, right? So sometimes, so this is a future money. This is a present money. So this is the P naught. Remember we use amount of money, right? So it's the same thing, but I don't know why this textbook, they rewrite it in another formula, that's fine. So let's see this one. Let's just keep using one formula. Okay, we don't need to try to remember another formula. We have amount of money equals to P naught raised by E times RT. As long as it's compounded continuously, we know we use this model. Okay. So we want to be able to have $5,000 in the future. And we want to find out how much money we need to invest right now. And the interest rate is 12% with a 0.12. And for 2 years, which is 2, right? So this P naught equals to 5,000 divided by E raised by 0.24. Right, just plug into the calculator, right? That's about $3,933.14. Okay, we don't really need to get into the negative exponent or another formula. We can still use the previous formula. Because the only thing is we're not finding the future amount or finding how much money we need to deposit now. Because this is quite useful, right? If you want to have, let's see now you're in your sophomore year, right? And you want to graduate, you are graduating in a couple of years. Or maybe you're making some little money and you're thinking, okay, in 5 years, I want to buy a car. And I know which car I want to buy. I want to buy the Tesla car, costs 50,000. Right? So in 5 years, I find a bank maybe offers me 5% interest rate. So how much money do I need to deposit now? Right? So this side will become a 50K. It's just, it depends on how they calculate the interest, right? If it's compounded continuously or compounded annually or monthly or daily, stuff like that. So right. So this formula is quite useful. Okay, now let's talk about the Euler number. Remember, we have this for compound period. So this is M compound period for any M compound period. So we have this, right, without this T. So we have 1 plus, well, that's the interest rate, right? You see, from here, MT, it become E to the RT. So this is a finite world, right? Compound annually, quarterly, daily, all finite numbers. But this is compound continuously, right? The infinite numbers. So what is the Euler number? What's the Euler number? EULER, Euler number. What is it? That's the Euler number. Okay. This is 1 plus 1 over m raised by m. Then take a limit, let m goes to infinity. Let m goes to infinity. So then, but then this is, too much to write every time. And also the mathematician Euler, found this pattern. So this been named after him, Euler number. That's it. So E represents the limit taking m to infinity of 1 plus 1 over m raised by m. Okay. Okay, so for chapter 5, we're only covering these 2 sections. And next video will be chapter 6.